So for lecture 9, let me check. Someone.有同学问，之前那页的 data loss 是指直参复制出来的对象，相比原来的对象数据少了。对，就本来我们其实是传递的是一个这个派生类的对象，对吧？但是呢，它接收的是个基类对象，所以呢，这个派生类对象呢传过去之后，其实它在这个传递过程中啊就被slice 掉了一部分，对吧 ？slice 掉一部分，对吧？所以算是其实是有一些这个数据的data loss， 对吧？相当于我们把一个派生类对象赋给了一个基类对象，那这个时候很显然这个就会有数据丢失，对吧？Okay, before class, we want to have one question for you. Okay, so the question is, let's have 2 minutes. The question is, what's the correct output of the following program? We have the class derived 1, and then so in class derived 1, we have the constructor and the destructor, which output something. And then we have derived 2, which is public inheritance of derived 1. And then we have the constructor and destructor. So in derived 2, we in the constructor, we call derived 1 constructor. And then in the main function, we define derived 2 object. Then our question is, what is the order of the destructor and constructor call? What is the order? Assign another 30 seconds. Sorry. Okay, time is up. Let's check the results. You can see here, most of the students get the correct answer. Some students may still need some time to learn this, the constructor and destructor call. So answer is A, right? Answer is A. So first is derived 1 and then derived 2 constructor. So first the base part will be constructed and then the derived part will be constructed. And then the destruction is in the reverse order of construction. Okay. Okay. We have another question here, but but I think because we learned multiple inheritance. However, this is we did not teach this in class, so we will not have this as a question. So I want you to have a guess on this. So in this example, we have the class base 1, and then class base 2, and then this is multiple inheritance, this derive, and then first parent is base 1, second parent is base 2, and then we have this derived object. Then we get a pointer, right? Pointer to the derived object. So first is point to base 1, and second is point to base 2, and then point to derive, P1, P2, P3. Then are the pointers equal or not? So we have this 4 options. So in this case, P1 and P3, P1 is this one, point to this, and P3 is point to this. They are equal. And then P2 is different, okay? P2 is different, points to a different place. This is, we did not learn this in last class, but I still want you to know about this, okay? So this is derived object, Then in the, if we try to get the base pointer of different parents, then this base 1, this is the order, it takes this order. So this is the first parent, second parent. So base 1 will be will have the same address of with derive, right? And then base 2 have a different pointer here. Okay. So this is the grammar related to multiple inheritance. Okay. Now we will learn something new. Polymorphism. So we just learned that. So the problem is if we try to call this function tune by a derived reference, then this will be the output, right? This will be the output because compiler know that, okay, it's already upcasted to instrument reference, so it should call this, right? Instrument play. So nothing wrong, right? But in real applications, we may want to have this because it is one object. Why it does not have one sound, right? So this is our requirement. We try to have this output. So how to do that? We have learned that we add a keyword virtual here, right? Add a keyword virtual here. Then this will be enable this polymorphism. So without virtual, it is called early binding. Right? Without virtual keyword, it is called virtual binding. So before this slide, all the binding are virtual early binding. Okay, are early binding. Before this slide, all the binding we have learned are early binding. So binding means we have a function definition. This is body. Either this is a member function or a general function. Then here are some function call. The binding is we try to bind the function body, right, to the function call. Right? So this is binding. So early binding means binding is performed during compilation before running the program. So the compiler, before compilation, the compiler will determine which function body will be executed when we have the function call. So our previous problem is that because we use early binding, so the compiler cannot know the correct function to call. Here, correct means we want, and because it's wind, we want wind sound, right? This is correct one. However, the compiler does not know that, right? Doesn't know that because it has done some upcasting, so it thinks it should be instrument reference. So you get instrument play, right? So this is the early binding and the problem. So now the solution is polymorphism. So we define or use a virtual keyword, and then this virtual keyword in the base class member function, we can use virtual keyword to declare the member function in the base class. Then this enables the late binding. Late binding means binding is done during runtime according to the original type of the object. So this is late binding. Okay, this is late binding. Okay, let's have 5 minutes break. Okay, let's continue our class. So we just learned that the problem was caused by early binding. And before this virtual keyword, before we use virtual keyword, all the function calls are using early binding. And this virtual keyword enables late binding. So late binding enables polymorphism. Okay, polymorphism in that by calling a virtual member function of a base class through a pointer or reference, and calling virtual member function. Then the function call will be resolved dynamically during runtime. Dynamically means depends on the exact object, right? Type or original object type, right? Or original object type. So this is polymorphism. And then we already know this override. Right? Override means redefine the base class virtual function in the derived class with exactly the same function name, same return type, and same arguments. Then to enable this polymorphism, we need to first we should use virtual, right? First we need to use virtual, and then we need to override the virtual member function in the base class. And then we need to use reference or pointer to call this member function. So this together enables this polymorphism. Without this, polymorphism won't work, okay? So when a function is declared as virtual, this is grammar. When a function is declared as virtual in the base class, it is automatically virtual in all the derived classes. No matter the derived class, in the derived class, because we will override this function, no matter we have used this virtual keyword in the derived class or not, it will be virtual, okay? So this is grammar. Then So solution to this previous problem, we already demonstrated that, right? Already demonstrated that is to use virtual keyword. Right? Then output will be wind play. Our question is, if we do not use reference, if we use object, will this work or not? Right? We still use virtual, and then we use object. Right? Does this work or not? So we just learned that if we try to provide a derived object where a base object is expected, then there will be object slicing. We know that, right? So our question is, does polymorphism work here or not? So the answer is no. Answer is no, because we just mentioned that polymorphism needs to work on reference or pointer. Otherwise, it won't work, okay? So this late binding or polymorphism only works for pointer and reference. Here's another example. So we have class instrument, then we have some virtual function, and virtual function, and virtual function, like this. And then in class wind, we override these member functions, virtual member functions. And then we also have percussion and stringed. These classes also override those virtual member functions. And then we define even more for this wind. We have brass and wood wind. The difference is that in brass and wood wind, we only override play and what. Play and what. We don't override adjust. Right? Adjust is not overridden. Right? Then we have some test. First, we have this tune. Right? This takes instrument reference. Then we also have an F function that takes instrument reference. Okay. Then we have an array of instrument pointers. Actually, we have some upcasting here. We are upcasting, for example, wind pointer to instrument pointer when we define this array. Then we can call this by a for, right? For like that. And for the space limit, we do not have that actually. Then for this part, we call tune, right? We call tune function. So for the tune function, we can see that because the tune takes the instrument reference, and then polymorphism all works. So because flute is a wind object, so it outputs wind play, like that. However, this flute horn is a brass object, and this F function calls adjust. So this we just know that flute horn is a brass object and it calls adjust. Then if we try to find adjust here, right? However, in brass, we did not override adjust, right? We do not have that version. So polymorphism will work in this mechanism. It will follow this inheritance diagram up, right, until it finds a definition of adjust. In this case, it will find adjust in this wind class. So it will output wind adjust. So although it is a brass object, it will output wind adjust. Okay, so this is how polymorphism works. Then we will learn more grammars related to this. First one is override. So this override keyword requires compiler to check, requires compiler to help us to check whether a member function in the derived class correctly overrides a virtual function in the base class. So this is for us for those careless programmers to avoid some bugs, right? So for example, in this derived class, if we have the override here, compiler will help us to check whether this function correctly overrides one in the base class. We can see here, it correctly overrides this one, exactly the same version, right? So compiler will pass this check. However, for this F1 in this version, we can see here, compiler will check whether in the base class there is a virtual function in this format. Then answer is no, right? Answer is no, because this is non-const. So in the base class, there is no such non-const F1 function, F1 member function. So there will be an error. So this is the usage of override. Then final can be used in combination with override. We already learned final before, so this is a kind of a review of final. It disables inheritance of a class or disable a member function to be overridden. So for example, if we have this override here in class B, and then in class C, if we try to override this F1, then there will be an error because we have final here. So this function cannot be override in derived classes. So this is keyword final that can be used in combination with the override keyword. Here's another grammar. This is default arguments values in virtual functions. So it basically says if we have a virtual function in the base class that takes a default argument, and then in the override function, we have another default value for I. This is 5, this is 50. Then the default value for this function call will all be 5. This is grammar. Don't please try not to ask me why. This is just grammar. Remember, memorize it. Okay. Then type ID help us to get the correct type of an object. For example, we have the carton here, define carton, and we upcast from carton reference to box reference. Then we can check the carton and the box, the class of carton and box, right? So the type is still carton, right? Although it is upcasted to box reference, it is still in the polymorphism the type of view from this view. It is still carton object, right? So the type ID output correct type of this object. This is type ID, and also calling the base class version of virtual function. This is, I think this is easy, not difficult to understand. So in the base class, we have this volume virtual function, and then this in the derived class, if we want to use the base class version, we can use the scope operator, right? We already learned this right before. If we want to call the base class version. we learn something related to static cast and dynamic cast. So this static cast is to cast statically. That means it is done during compilation, right? So the cast is checked statically when the code is compiled during compilation. So it converts the derived class pointer or reference to a base class pointer or reference. So if we have this class diagram, these are the derived class of box, carton, and the zero pack. Then we can do this kind of cast, right? So well, we already did that, I think. So first we define a zero pack object, then we can upcast this zero pack a pointer to a carton pointer, right? Upcast. So the carton pointer actually points here. This is object view, an object view. And then this is direct base of zero pack. This is direct base, is carton. And then indirect base is box. We can still cast it to this. So in this case, this static cast is not needed. This keyword is not needed. We can directly assign, right, the pointer to the base type. Right. So this is casting upward the pointers. We can in another way, we can cast downward. So for casting downward, we convert a base class pointer or reference to a derived class representation. Still for this inheritance diagram, if we have a carton object, which is already upcasted to a box pointer, this is a carton pointer, we can use static cast to cast it back, right? Cast back to carton, right? Because it is originally a carton object, right? So we can cast it back. However, because it is carton object, if we want to cast it to a zero pack object, that will be error prone or indefinite. Probably there will be bugs. So if you cast downward on the pointers in this class diagram, in this downward direction, be careful about that, and there may be some errors. So this static cast in this case is not safe. So some of you may also know about this C-style cast, right? Because we have already done that for built-in types for casting, for example, for float value. We can cast it to an integer. I think there is a question. Are the members in carton remains when casting? I think so. I think so. Carton to box and to carton. I think so, because we already have some example on that, right? Because we can cast it and then we can do polymorphism. Otherwise, that may not be possible, right? So I think the member function, the members are not lost in this case. Okay, members are not lost, but because we are casting from, in this case, we are casting from a smaller object, carton, to a larger object, serial pack. So what's the data here, right? So that will be indefinite. We are casting from a smaller object to a larger object. So that's will be erroneous. Okay, then for dynamic cast, it is applied to pointers and references to polymorphism class types. So in this case, there should be virtual keyword in the member functions in the classes, right? So there at least one virtual function, right, in the classes. Dynamic cast works for this polymorphism, right? So be careful about that. Be careful about that. So dynamic cast is safer than static cast because it is done during runtime, and if the cast fails, a null pointer or zero pointer will be returned. Because previously, for this example, results are indefinite. There may be bugs, right, if it fails, but we don't know that. However, in this case, in this example, if we do dynamic cast, in this case, then we can check the pointer. If it is null pointer, then it is not null pointer, we can do something, right? So in this sense, it is safe, right? It's safer than static cast. We can also apply dynamic cast to a reference parameter. First, this one is on a pointer, right? It's on pointer, and then we can also work it, make it work on reference. However, if we cast on reference, if the cast fails, execution function of the function will stop, and there will be a exception 0. So exception, we do not have time to learn exception in class. For now, we can know that if an exception is thrown during execution of the function, then the program will stop. This causes bad user experience, right? Because the program crashes, right? So casting, dynamic casting on reference may not be so good compared with pointers, right? Because for pointer we can check if it is 0 or null pointer, we just avoid it, right? We do not do something. That's fine. The program will not stop or crash, right? Then for this, there are still two ways. Actually, also two ways of dynamic casting. One is downcast. Downcast, for example, we have a serial pack pointer, which is first upcasted to this box pointer. Then we downcast, right? Downcast from the box pointer here, downcast from box pointer to a carton pointer. Then it works. And also, because it is a serial pack object, we can we can cast this pointer to this content pointer, right? Contents pointer. It also works because this object is a serial pack object. In this object, it has all the parent objects: carton object, contents object, box object. These sub-objects are all in the serial pack object, so there will not be a problem. Okay. So there's this also mentioned about this virtual keyword. So dynamic cast works for virtual member functions or classes with virtual member functions. Okay. So these are the grammars related to static cast and dynamic cast. And then we will learn this virtual table, how the compiler implements this late binding. Okay, so for this virtual table, it is a table for each class to store addresses of the virtual functions, which is created during compilation. So the virtual table is created during compilation, and then it is stored in the object during runtime. So each object of the class with a virtual function consists of a pointer, right? Consists of pointer called vptr or vpointer, pointing to the vtable structure. And the vpointer is stored at the beginning of the objects. So for virtual function call by the base class pointer, the compiler inserts code. So this during runtime. During runtime, compiler inserts code to obtain the vptr and vtable for the function address. So the object will be constructed and the vptr will be inserted into the object. So when we do function call, then based on the pointer, we can find the vptr and then we can find the vtable. So in summary, during compilation, the compiler determines the contents of the vtable, and then during runtime, vtable structure is created in the memory, and then the vptr is stored in the object. Then when we call this virtual function, we can find the virtual function by the object. From the object, we can find the vptr. From the object, we can find vptr, and then from the vptr, we can find the vtable. So here's an example. So we have this class B, and this is base class. And then these are the virtual functions, and there are two variables. We have derived class, which follows is a relationship, public inheritance, and then we overwrite one function. Right? Then we define a base object, a derived object, and then we do upcasting on the pointer, and then we call this function 1, right? Because this is a upcasted pointer, so when we call this function 1, polymorphism will work, right? Because for this function 1, it's virtual, so it will work. So because it works, so there will be a virtual pointer and virtual table constructed when during runtime, right? So anyways, for all the functions, for all the member functions, it will be stored in a memory segment. This part, for example, all the functions of different classes will be stored here. And then the virtual table will be constructed. The virtual table will be constructed for each class. Each class will have a virtual table. So for class B's virtual table and class D's virtual table, they will point to different functions. Here, we can see that because in this D's virtual table, we already defined function 1, so it will point to this function 1. However, we did not define function 2, so in this virtual table, the function 2 will point to B's function 2, because we did not define that, right? So when the constructor, when the virtual table is constructed, yes, these functions are actually function pointers. These are pointers. They point to the the real function, right? Real function. So these are the pointers. These are pointers. So the virtual table is not very large. Okay. Then for this object B, when we construct this object B, there will be virtual PTR, virtual pointer, virtual pointer. So this virtual pointer will point to this B's V table. And then if the object is B's object is B, then if we want to call the B's virtual function, then it will call in this way, right? If we want to call function 1, then it will find this B's function 1, function 2, B's function 2. Right? And then for object D, the virtual pointer will point to this virtual table. And then if we want to, for example, if we want to call function 1, then we'll call this function 1. Right? So in this way, we enable this polymorphism, right? Polymorphism. Although we have done this upcasting on this pointer, right? On this pointer. However, from the object, this VPTR points to this V table. So we enable this polymorphism. It still calls this function 1, right? It still calls this function 1, like this. Right? So this is virtual table and virtual pointer. And then here's an example. We can see here, if we want to test whether there's a virtual pointer. Oh, this is a very good question. If we want to access the virtual pointer, I think there should be some way to crack it, because we know that the virtual pointer is stored at the beginning, right? Virtual pointer is stored at the beginning of this object, right? So you should have some way to do some casting, right? You can static cast or cast this part of the value. Then you can get a pointer value, right? So I think there should be some way to print, hack this code and print the value of the virtual pointer, okay? Because we know that it is stored at the beginning of the object. Then in this example, we have this class no virtual, and we have one virtual function, and we have a class with two virtual functions. Then we will print the size, print the size of integer, no virtual, and one virtual, and two virtual. So the results are different for different machines. For 32-bit machines, we have this result. The major difference is pointer size is different. So for this 32-bit machine, we can see that the pointer is 4, and then int is 4. Here's an int, right? Here's an int, and here's an int. So if there's no virtual, there's only a integer, so the size of the class is 4, right? When there are some virtual functions, the size of the class will be 8. That is 4 plus 4, right? It's one member plus the virtual pointer. And then for the 64-bit machine, we can see here we have still one member takes 4 bytes, and then the pointer takes 8 bytes. So it should be 12 bytes, right? 12 bytes. Why it is 16 bytes? Why is that? Because for this 62-bit machine, 8 byte will be aligned, right? 8 byte will be aligned. 8 byte. This is 64-bit, right? So this is memory alignment. So this part is the integer, and this part is a pointer. Right. Sorry, maybe I'm wrong. This part is pointer, right? We just mentioned that pointer, the virtual pointer is at beginning, right? So this part, first part is pointer, and then second part is integer. However, this part is not taken, right? This part is alignment by the alignment. This part is wasted. Okay. So this is by this example, we know that there are indeed virtual pointers, and it takes some memory, right? Takes some memory. So I have one question for you for this example. If there are for multiple inheritance, right? Sorry. Harry. For multiple inheritance, what is the size? Right. I want you to have some test. You can write it. Write an example, very easy example to have multiple inheritance, and check the size of the classes, right? And try to understand it. Right? Try to understand it. Is there a single virtual pointer or multiple virtual pointers in this case? Okay. Okay. From next class, we learned to this abstract class. We learned classes and inheritance, and then composition, and then polymorphism. Right? We have learned polymorphism. Now abstract class. So in the instrument example, class instrument does not define objects. It just provides some interface, right? So only the class wind defines objects. This instrument actually do not need to define objects, because this instrument actually do not have sound, right? So this is just a general idea. But class 1 can define objects because you can play some sound, right? So actually, an instrument can be defined as a abstract class. What is abstract class? How to define abstract class? This depends on this pure virtual member function. So this pure virtual member function can define abstract classes, and also using this pure virtual member function can be we can prevent, because abstract class, if we do not want abstract class to define objects, this is a way. So in this case, we only provide interfaces for the derived classes, and also actually this abstract class, the interface for abstract class is also an interface outside. For example, we have some interface here. This is the abstract class interface, so that another user can use this at the interface. So this is abstract class here, and then these are the concrete classes. So this is wind here. This is the instrument. So we will learn this later when we learn design patterns. And abstract class provides us a way to provide interfaces to others. Okay, we will learn this later in more detail. So the grammar is that this is the grammar for defining pure virtual member function. The only thing we need to note is that equal 0, right? This equal 0 sign. So a class, so an abstract class is a class with at least one pure virtual member function. Okay. What's this? Okay. So abstract class, we just mentioned that it cannot define objects, only provides a way. What's this? Sorry. Oh, it's the keyboard. Why the keyboard pops up? Okay. It only provides a way interface for derived classes, and in this case, in this way, we can avoid object slicing because in this way we can avoid the objects to be passed because if we for example, if we take for example here, if we have this function, why is this? Sorry about that. I don't know what happened. This keyboard, why it pops up? Okay. So this in this case, if we take this object here, so let's check what happened. This one, maybe close it. Okay. So because we have defined a pure virtual memory function here, so this class is an abstract class, right? So in this case, an abstract class cannot define objects. Cannot define objects. Like this. If we try this, for example, if we try this function, if we want to call this function by flute, then we learn that in last class, object will be sliced, right? This flute will be sliced to the instrument object. However, because it is already abstract class, this will cause companion error. So in this way, abstract class avoids object slicing. So we can never have a base class object in this case. So it avoids object slicing. Okay. Then there are some grammar related to abstract class. So for a derived class, of an abstract class, it is still abstract if the inherited pure virtual functions are not defined. So in the derived class, if we do not define this virtual function, then the derived class is still pure. It is still abstract. That means it still cannot define objects. And the pure virtual functions may have a function body in the base class. We can still define some function body, but these functions still need to be overridden in the derived class so that the derived class can define objects. Otherwise, it cannot. So no matter with function body, okay, no matter with function body or not, the abstract class cannot define objects. Okay, this is for the base class in this one, right? It can have a function body, but it cannot have objects, cannot define objects. Yes, you can define object, the function body for this pure virtual function in the source file. Okay, in the header file, you still have this equal 0, right? Declaration. Then in the source file, you can define the function body for this function. And this forces the derived class to override pure virtual functions before defining objects. Right? Here is an example. So you can see here, we have class pet. These are pure virtual member functions. However, we can still define the function body, right? Like this. And then in this class dog, if we do not define the function body for the pure virtual function, then there will be companion error. We cannot define objects. If we define the function body here, then it will work. Okay, so this is the abstract class and pure virtual function. So the key idea is that abstract class provides some interface, right? Provides some interface, so that we know for this class hierarchy from pet to the dog, all has this kind of interface, all has this speak, right? And all has eat. Then users can access this interface. So abstract class is basically used to define interfaces. Okay. Then there are some grammars for constructor. For objects of classes with virtual functions, the compiler secretly inserts code into the beginning of the constructor to initialize the VPTR. So we learned VPTR before. So the constructor, right? This is the compiler do that in the constructors, right? In the constructors to initialize the virtual PTR. When calling a virtual function in the constructor or destructor, polymorphism does not work. So this is grammar. Because the object has not been fully constructed, polymorphism cannot work. So if we, in this case, we call a member function, or especially if we call a virtual member function, local version will be called, local version of the current class, where the constructor is defined. If we call the local virtual member function in the constructor function body, then local version will be called. No polymorphism. Okay, so in contrast, when calling a virtual function in other member functions, polymorphism works. This we will have an example later. This is interesting. Other function means this other member function, maybe this member function is not virtual. If we call a virtual function in a non-virtual function, then polymorphism still works. This is interesting. Okay. Constructors cannot be virtual. It cannot be virtual. And however, destructor can be virtual. And destructor can be virtual. And also, we can also have a pure virtual destructor. So by defining a pure virtual destructor, we have an easy way to define an abstract class, right? Because destructor is also a member function. So if we have a pure, as long as we have one pure virtual member function, we have the abstract class. Okay. So for this pure virtual member, for the pure virtual destructor, the function body still needs to be defined because it is destructor. Right? For this destructor, anyway, we have to define the function body. Right? When there are no other pure virtual functions, this gives a way of defining abstract class. So if we want to define an abstract class, an easy way is to declare a pure virtual member function. A pure virtual destructor. So the design principle is that in polymorphism, the destructor is typically declared virtual to avoid memory leaks. Be careful about that. So we will have an example later and show you why this is the case. And whenever there is a virtual function in a class, a virtual destructor needs to be defined. So be more careful about this. Okay, if you have a virtual function in a class, you should have a virtual destructor. Be careful about that. Otherwise, there may be memory leaks. Okay. So here is an example. Let's check. We may have some code for this. Okay. A virtual destructor. You can see here, this is the example. Actually, it's exactly the same function or same code as the slides. So this is the base class, and this is the derived class. You can see here, there's no virtual, right? So there's this is not polymorphism, right? So base 2 and derived 2 are virtual. Base 2 is virtual, right? Base 2 is virtual. Then derived 2 is automatically virtual, okay? Because we in the base class, the structure is virtual. And then we create an object of base 1. Actually, this is the derived 1, and the upcast the pointer to derived 1 to base 1, and then we delete it. And then we have a derived 2 pointer upcasting to base, and then delete it again. Let's check. Which destructors are caught, right? You may have a guess what will happen in this case. I think this is very interesting example. Sorry. So we can see here. So when we delete derived 1, actually only base 1's destructor is caught. Derived 1's destructor is not caught. Because of what? Because it has been upcasted to base 1, because there is no virtual, right? Destructor is not virtual for derived 1. So the compiler will think, okay, this is base 1 object, so it calls base 1's destructor without calling derived 1 destructor. In this case, some memory, if there are some pointer members in derived 1, then there will be some memory leaks because this destructor of derived 1 is not caught. Okay, so this is the problem. Derived 2 works correctly because we have this virtual here, right? For base 2, we have this virtual here. Then destructor is automatically virtual. Then if we want to delete the base 2 pointer, actually polymorphism works. So it knows, okay, compiler knows, okay, now we need to delete, a derived 2 object. So derived 2 destructor will be called first. Okay, so this is I think this is very interesting and important example. Remember that when you have virtual functions in the class, you should have a virtual destructor. Have this virtual here, right? Do not forget it. Otherwise, there may be some memory leaks. Okay. There are some notes on polymorphism. To avoid runtime memory overhead, only use virtual functions whenever necessary, or when necessary, only when necessary. This is because polymorphism consumes more runtime and more memory. Why? Why more runtime and more memory? Because of the VPTR, right? And vtable. And vtable, right? So because of this, it takes more memory, right? For sure, right? And if we want to call the virtual functions, then there are some, addressing, right? From VPTR to vtable, and then from vtable to the functions, right? More addressing, right? More addressing. So it's more time consuming, more runtime. So if you use polymorphism too much, then your program will be slowed down. So be careful about that. Okay. So this is actually we already know that by calling virtual function with base class pointers, differences between objects of different derived classes are expressed with different behavior. So we already know that. So this is polymorphism, and public inheritance indicates similarity between the base and derived classes or derived objects. And the virtual function indicates difference between them. Because this public inheritance, by public inheritance, both base and derived objects have same interfaces, and they have similar functions, actually, right? However, if we have this virtual function, then different virtual functions may have different behavior. So there may be different outputs, right? One more example. From this example, we can see here. This is an animal class, and we have member function action. Right. This is not virtual, right? We can see here, not virtual. However, speak and motion are both virtual, right? Then we have a bird, and we have virtual function speak and the virtual function motion. Also a fish have the virtual functions, right? Now let's check if we call this function, which will be the output if we call this function. Fish function, bird function, fish action, bird action, what will be the output? Will this animal speak, or will this bird sing or bird flying be output? Actually, here, polymorphism still works. Polymorphism still works. So we know that this should work, right? Because we are using pointers, right? We mentioned that pointers and references are important for enabling polymorphism, right? However, this still works. This still works. So be careful about that. Okay, so because this is in action, this we call the virtual functions, then polymorphism still works. Okay, this is because the VPTR, right? If you want to understand this, I suggest you to try to think about it from the VPTR. Right? Okay, now we have a more complicated example. So in this example, we want to define or design a shape class with virtual function dump. So that the derived classes of shape only need to override dump to customize the output. Here, two derived classes are implemented, point and rectangle. So we can see here, this is shape. So we have this class shape, and then we have this virtual function dump. This by assigning it to 0, we have a pure virtual function, right? Pure virtual member function. And this takes a very special parameter, O-stream reference. Then we have this friend again. We mentioned that friend actually, in most cases, are not necessary. This keyword are not necessary actually. If we do not have this friend keyword, we just define this function outside of this class. It will be fine. Actually, this function still is still defined outside, right? Outside of this class. You just declare this function in the function body. In the class body. And then we have a virtual destructor. So this is to enable like this, cout shape object S, right? To enable this. Then we can guess that in this operator call, it will call this dump, right? It will call this dump. And this is the friend function. So this is actually a general function defined outside of the class. And then this stream operator, we ask you to memorize this format or this grammar, right? So this is how we define all the stream operator. And then as we guess, this dump will be called here. And then this is return. So this return, we have learned this before. This return means we can do this. Otherwise, without this return reference, we cannot do this. We cannot do this. We can only output 1. Okay, so this is O-stream, the stream operator, and then in the class point, we have some constructor, and then we override this virtual function dump, and this is destructor. So by overriding this one, we can customize output format. Customize output format. So in this way, we do not need to write another O-stream, write another stream operator overloading. We do not need to write this. And then we have the rectangle class constructor and also override dump, right? This is how we customize the output of the rectangle object. Now we have the main function. The main function. Then we can use either file output or the standard output. Both of them works because this file out object and the cout are both objects of the derived classes of O-stream. So by calling this function in this way, actually we are doing upcasting, right? Check about this. If we call this function like this, actually we are calling operator file out and point, right? When we call this function, we know that we only defined one operator, right? One operator, which takes OStream reference, right? OStream reference and shape reference, right? So in this case, both objects will be upcasted. So upcasting is performed here. Both of them are upcasted, okay? Then the friend function will be called. The friend function, this friend function, this one. So this one will be called. This one will be called. Now we have OStream reference, we have shape reference. So then shape.dump will be called. And that means we will call this dump function, right? By this call, we will call the dump function. Now polymorphism will work because it is point actually. So it will call points, this point objects virtual function, dump. We'll call this function, right? So in this case, we will call point dot dump it will call point dot dump file out, right? Essentially, it will call this, right? Oh, what happened? Okay. Okay, so this is the example. Essentially, it will call point.dump, right? We have this example. We have the example here. Let's check. We can make it. So we can test it. So we can see that there's an output, right? So we by running this program, we both print some message to the standard output, that is screen, and also print it into the file. This one, right? So I think this example is interesting. I hope you to try to understand what happens, right, when we call these two functions. Try to understand it. Polymorphism works here. Okay. And this provides an easy way of formatting the output for all the derived classes, right? So you just need to define dump, right? Dump function, right? It's a very interesting example, I think. Try to understand it, and also in the future, if possible, you can try to use it. Okay, and this is all for this slide. I've learned virtual function and polymorphism. This, I think, this most critical part of this OOP design, and the most interesting and most difficult part. And VPTR and VTable are the enabler for the polymorphism. And the abstract class actually defines some interfaces. We will learn this in the next class. Okay. So virtual destructor is very important if we want to avoid memory leaks. Okay. So this is this slide. Actually, this is the the ending or the end of this basic grammars. There's some more parts about this on Lambda. However, Lambda functions and the template are different from this OOP design grammars, right? So this is the end of OOP grammars, I think.